If one, for example, rotates a square 90 degrees, then you will get back the same square. So you say that the square here have a 90 degrees rotation symmetry. It means that the map that will map it 90 degrees clockwise rotation, that's a symmetry for this figure. And if 90 degrees is a symmetry, then also multiples of 90 degrees. For example, 90 degrees in the other direction or 180 degrees. If you have an equilateral triangle and rotate it 120 degrees, it will also have a rotation symmetry. So rotation around the center of the figure. There are also other kinds of symmetries. For example, if we take a mirror image of this square in this line, the center line, or in this line for that matter, we will get back the original square. So it also has a mirror symmetry in these lines and also in the diagonals. So it also has a mirror symmetry in these lines. Also here for the equilateral triangle we have symmetries in lines. So if you mirror in this line or this line, so it has mirror symmetry in the angle bisectors. These two figures do not have translation symmetry, because if you translate this figure, you will get back the same figure, but it's moved a distance to the right or left or somewhere. And for it to qualify as the same image, you shouldn't be able to tell if anything has happened to the figure or not. And if you move it some distance, you will be able to tell what's before and after the translation. So it does not have a translation symmetry. If you want translation symmetry, then you should have a figure that will repeat the pattern infinitely. So if you put happy faces, identical happy faces, infinitely many, it will have a translation symmetry. And the translation symmetry will be with vectors going between two corresponding points of these two faces. For example, between the centers of the two faces. And you can also take vectors between two faces. So here it has translation symmetry with these vectors. Then it also could have combination of mirror and translation symmetry. For example, if you have infinitely many balls like this, then it will have a mirror plus translation symmetry in this line. So for example, if you take a point here, take the mirror image and then translate it with the vector going through the two centers, then we get back the same figure, lidspelling in Norwegian. If you have a map that will rotate 90 degrees, then the inverse map will be a rotation in the opposite direction, so 90 degrees in the other direction. Then if you call this mapping A, then you call the other one the inverse map, and you denote it by A minus 1. So if you first do the map A and then do map A minus 1, the inverse map, you just get back the original figure. So the inverse map undoes the map. The identity map is a mapping that just leaves the figure unchanged. You can denote the identity map with I. So for all points, you just give back the point. If you combine two symmetries, for example, U and V, that will also be a symmetry. If you have a symmetry W, then also the inverse of that symmetry will be a symmetry. And the identity map is also a symmetry. So in this way you can make new symmetries if you have symmetries.